Welcome, this is Coach Dorf. Today we're going to talk about the product rule and the quotient rule. Before we begin, let's do a little bit of a review. So what is the meaning of the derivative? Well, we've talked about that it can be thought of as the slope of the tangent line. This often occurs when we're looking at the graph of a function. So, for example, here, I draw the graph, my function be y equals f of x, shown here in blue, and I have a point x equaling a there, and I bring that point up onto the graph there of my function. Then drawing in the tangent line that intersects that red point on the blue curve at one point locally, then that slope of that line is the derivative at the point A. So that's one way of thinking of the meaning of the derivative. And that occurs often if we have a graph of a function. Another way is that the derivative equals the velocity. And this happens if our function represents either the distance or position of a particle or an object. So if we have a description of a function that either as a formula or as a written description, and it represents a distance or position formula, then the derivative is the velocity, and we note that the second derivative would then be the acceleration. And you can also see these if an object is moving, such as throwing an object into the air. That's an example of this type of problem. The third description of the derivative is rate of change. And we're going to talk about an example of this in just a moment. But before we get into that, I just want to review also the power rule. Last time we talked about the power rule, and that is if I have my function that can be represented as x to the n, where n is a real number, then the derivative is going to be nx to the n minus 1. And an example of this, real quickly, would be that if f of x equals 3x to the 5th, then the derivative, I would bring the exponent 5 out front, multiply it by the 3 to get 15x, and then I reduce the exponent of 5 by 1 to get a 4, like that. Okay, now we can apply this to a really cool example that I want to share with you. And this has to do with a circle. So if I have a circle, I know the area of the circle is, we're going to call it A of r here, and that's going to be pi r squared. That's the formula for the area of a circle. Note that r is my variable here. So as r increases, then the area increases. And if I let's draw a little circle here, there's my circle, and there's my radius, and the area is going to be just that part in there. And just so you all can see that that's a circle. Okay, so what is the derivative? What is the derivative of this? And so that would be I can write that as dA dr. Well, by the by the power rule that we talked about last time, I bring that exponent. Here's my function. To take the derivative of that, I'm going to bring the 2 out front, and then write pi, and then reduce the exponent on r to be by 1, so I get 1. So I get this. That is the derivative. Well, what is that? That is the circumference of a circle. All right. So we're saying that if we take the derivative of the area of a circle, we get its circumference. That's totally unexpected. Why is that? Why does that happen? Why is it that when we take the derivative of the area of the circle, we get its circumference? All right. Well, let's explore this a little bit. So if we think about derivative as being rate of change here, and let's think about this as like, if it's raining outside and you have a lake and a drop of water hits the lake, what does it do? It makes a circle in the water on the lake, and then that circle increases and increases and increases. Okay. That then represents what we have in this type of situation. So here's my circle, and it has radius r, and as it's increasing, we've got a larger circle, and then we've got the original circle. So my original circle here is r, and we're going to call this new part here, we're going to call that an h there. So the new radius, so we'll put down here old radius equals r, new radius is going to equal r plus h. So just a little bit more. And then what's the area? What's the area of the new circle? What's happening here? Well, that new area over in here is going to be this part here. It's a ring. So we can get this ring, and as the ring, as h, okay, there's our h there. That's that new, that little part that's added in that ring there, that width of the ring. As that goes to 0, then the new amount, or the new amount of area goes to this thin ring around the original circle, and that's going to get closer and closer to the circumference of the original circle. So again, if we look at that blue area here, as h gets smaller, that blue area gets, the ring gets smaller and smaller. And what does that area, that blue area approach? It approaches the circumference of the circle. So what this means then is that the rate of change of the area of the circle equals the circumference. That's just really cool. All right. If I write that in terms of our formula here, then ddr of the area, which is going to be ddr of pi r squared, is going to equal the circumference. The derivative of the area of the circle equals its circumference, because using the power rule, also we can see that that's 2 pi r. All right. Math is cool. That's just so surprising to think that the derivative of the area with respect to the radius equals the circumference. And it's because of the rate of change there. That area, that's the new part, that blue ring that's around the circle, as that gets smaller and smaller, it approximates the circumference of the circle. Who would have thought that at the beginning? I just think that's really cool and surprising. And that's one of the reasons I like math, because there are these surprising things that are just really, really cool. All right. So last time now we talked about the power rule. So today we're going to talk about two things: the product rule and the quotient rule. And the product rule is going to be, what is the derivative? If I have two functions, what is the derivative of their product? Of the product of two functions. All right. So let's see, let's just look at an example here before we tell you what it is. So suppose I have a function h, and I'm going to call it x squared times x cubed. What is its derivative? What is h prime of x there? Well, at first, we may guess, or we could hope, that the derivative would just be the derivative of the first times the derivative of the second. So we would guess that maybe h prime equals the derivative of the first times the derivative of the second. Okay, so in this case, if that's the case, then we would get 2x here by the power rule for the first one, and 3x squared for the second one. And if I multiply those together, I get 6x cubed. Okay, is this correct? No, it's not. That's not correct. Why do we know that? Well, notice that I can write h as I've got x cubed, x squared times x cubed, so that's the same as x to the fifth. And we know by the power rule that the derivative should be 5x to the fourth, right? Because I've got my exponent here, I bring that out front, reduce it by 1, so I get this. But that's not the same thing as this. So those aren't equal. So what does that mean? Okay, this means the derivative here does not equal the derivative of the first function times the derivative of the second function. Okay, so this is not true. Just don't want you to be confused here. Not true here. Okay, so what is it actually? Well, this is what the product rule says. Product rule says that if I have my function h and that equals f of x times g of x, then the derivative is going to be the first function times the derivative of the second plus the second function times the derivative of the first. And so there we've got this product rule there. And if we do the example that we just looked at, all right, for h of x equaling x squared times x cubed, then the derivative by the power rule, I'm going to get the following here. We'll get the first function, x squared, times the derivative of the second. Let me change my little nib on my pen here. Okay, plus the second derivative, second function, times the derivative of the first. And now if I simplify this, I get x squared. Derivative of x cubed would be 3x squared, plus, and then I write the second function. The derivative of the first one would be 2x. If I simplify this, I'm going to get 3x to the fourth plus 2x to the fourth, and that's going to equal 5x to the fourth. And that's correct, okay? And we notice that h, if it's x squared times x cubed, that's x to the fifth, and by the power rule, h prime is 5x to the fourth, and these are equal. Okay, that doesn't prove that this is right, but it just demonstrates that this is a correct, that this works in this particular case here. So what's the takeaway here? So first takeaway is what is the product rule? The product rule, again, can be written as if I have a function that's written as the product of two functions, and they're both differentiable, then the derivative is equal to the first function times the derivative of the second plus the second function times the derivative of the first. Okay, so that's the product rule. That's the first takeaway. The second takeaway is a little more subtle thing, is that just because something is convenient, just like we thought maybe at the beginning that the derivative might be the derivative of the first times the derivative of the second, that would be convenient, be nice, but it doesn't work. So when you do the math, you have to make sure the math works. Okay, for example, there is that example that at one time over 100 and some years ago, in the state of Indiana, people, one of the legislators wanted to dictate the value of pi would be 3. Why did he want to do that? Because 3 is a nice number. Pi is equal to 3.1415926, and it goes on forever. That's not so nice, not convenient to do. So he wanted to change that to make it 3, but it doesn't work. You can't change that. It doesn't, just because you want it to be nice doesn't necessarily mean it works well. Sometimes math is really beautiful, like this example I gave earlier about the derivative of the area of a circle equals circumference. That's really cool. Sometimes though, math is a little bit more complicated, but it always works, and we want to make sure that it works. All right, so let's go back and do an example, another example of this product rule. So let's differentiate the following function. We're gonna have y equals x cubed e to the x. All right. Now, the example I did earlier with the x squared times x cubed, I could do the power rule, and it was a lot easier to do the power rule than to do the product rule. Here, though, I have to do the product rule. There's no way I can use the power rule to do this one. I have to do the product rule. Okay, so let's look at that. Okay, so by the product rule, and again, we have to do the product rule because we have one function times a second function, and there's no way to combine them. So the derivative is going to equal the first function times the derivative of the second function plus the second function times the derivative of the first function. All right, so now I can simplify these. I've got x cubed, the first function. Now the derivative of e to the x is just e to the x. All right, plus my second function times the derivative of the first. What's the derivative of this? By the power rule, that's 3x squared. Okay, so now I do some simplifying. I get x cubed e to the x plus 3 e to the x squared. And that's a perfectly fine answer. But sometimes the book, or if it's a multiple choice question, they will take out what's in common. So you could also take out what's in common. They both have an e to the x. So we'll take out an e to the x. And they both have x squared. They have some x's here. The most they have in common is an x squared. All right. So if I do that, I take that out, then what I have in the original one here is I'm left with an x, because I had an x cubed originally and I took out an x squared. And in the second one, I'm left with a 3. So I bring that out here. So another possible answer is to write this as e to the x squared times x plus 3. Either of these answers is correct, but it's good to see that both of them are correct, and you can go about, and then you know how to go back and forth between the two. Okay, let's do another example here. So here I'm going to say let f be a differentiable function, and I'm going to call y to be x squared times f of x. All right, and the goal then is to differentiate y. Now, some of you may say, well, this one, I don't know what f of x is. That's okay. We're just going to do this. This problem's a little bit more abstract. We're just going to do it by doing the power rule. sorry, by the, my mistake. Okay, we're going to use the product rule, not the power rule, product rule. Okay, because what do we have? We have one function times another function. So that's why we're going to do the product rule. So the derivative is going to be the first function, the one in red, times the derivative of the second function. And I'm going to use, sometimes I'll use this ddx to mean the derivative. Sometimes I'll put the little prime or tick mark up above to represent the derivative. But in this case, I'm just doing the ddx. Okay, so we did the first times the derivative of the second, plus the second, f of x, times the derivative of the first. All right, so then what is ddx of f of x? That's just f prime of x. And then I've got the second times, and now I've got, what's the derivative of x squared? Well, I just use the power rule there, and I get 2x. And then combining those terms together, I get x squared f prime of x plus 2x f of x. It's customary to usually put the f and the f prime second there. It's perfectly fine not to do that, but usually that's the way that it's written. And if I wanted to, it's also possible to factor out an x that they both have. So if there's an x here, which is really an x squared, and there's an x here. Okay, so when I factor out that x from the first term, I'm left with an x f prime of x, so that these x times x here gives me the x squared that I had up here. And when I factor an x out of the second part here, I'm left with a 2 f of x. So either answer is correct there. All right. So that's the product rule. Again, let's just write it this way. I can write it kind of a shorthand way by going f times g, f of x times g, with the little mark up there, which means the derivative. And that's going to be the first times the derivative of the second plus the second times the derivative of the first. That's the product rule. Whenever we have two functions multiplied together, we're going to use that. Okay, now we've got the quotient rule. What's the quotient rule? When do we use the quotient rule? Well, that's when we have the quotient of two functions. So we have the quotient of two functions. And what does quotient mean? That means that there's one on top of the other. So it looks something like we have f of x over g of x. That's a quotient there. Okay, so the quotient rule says that in such a case, if both f and g are differentiable, then let's write that down, if f and g are differentiable, and well, I don't need to put an end there. Okay, sorry, let me backtrack a little bit. Okay, then I'll just do, then the derivative of f of x over g of x is going to equal the denominator times the derivative of the top minus the top function times the derivative of the bottom, all over the denominator squared. Okay, there we go. That's the quotient rule. Now, it's a little bit confusing. Again, this is an example that we would like it to be nicer, but it's not always nice. But this is what works, okay? If you want to see a justification for why this works, you could look in the textbook and they give you a proof of this. In my next lecture, I will give you kind of an intuitive approach why the product rule works. using the same idea I did today about the rate of change with that circle, okay? But you'll have to wait for tomorrow's video, the next video to see that. So let's look at an example here of applying the quotient rule. All right. So we're going to differentiate the function f of x equaling 3 minus 2x all over 5x plus 1. Okay. So the derivative of f is going to be, so I have to remember this, it's the denominator, so 5x plus 1 times the derivative of the top. So I'm going to write that, instead of doing the ddx, I'm going to put the 3 minus 2x in parentheses with a little mark on top, okay, which means the derivative, minus, make sure you do a minus and not a plus here, minus the top times the derivative of the bottom, all over the denominator squared. Okay. So then we'll simplify this, 5x plus 1, the denominator, times the derivative of the top. If I look at the top part by the power rule, the derivative of 3 minus 2x is just going to be minus 2. So then minus the numerator, the top, times the derivative of the denominator, which was 5x plus 1. The derivative of 5x plus 1 is just 5, all over the denominator 5x plus 1, quantity squared. Now I'm going to simplify this a bit. Remember, I'm going to distribute this -2 to both terms here. So I'm going to get negative 10x minus 2. And I'll keep that in parentheses, minus parentheses. Now I'm going to distribute this 5 to both parts here. So I get 3 times 5 is 15 minus 10x. Keep that in a parentheses, all over the denominator squared. Now notice I have this minus here. I haven't distributed that yet, but I'm going to do that now to both terms here. So when I do that, I'm going to get negative 10x minus 2 minus 15x. And then when I distribute this to the 10x, it's going to be plus 10x all over 5x plus 1, quantity squared. And then I see that the negative 10x and the 10x cancel out. So I get negative 17 over 5x plus 1, quantity squared. And there's my answer there. Remember, when you do the quotient rule, don't get the top and the numerator and the denominator mixed up. It's always the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. Also remember, it's a minus there, okay? All right, let's look at another type of problem that you could see. So let g of x be differentiable, and I'm going to let f of x equal x squared over g of x. Okay, so similar to a previous example we did in the product rule, except we're going to add a little bit of complexity to this one. I'm going to tell you that g of 1 is 2 and g prime of 1 is 6. And you're supposed to then determine the value of f prime of 1. Okay, f prime of 1. So in doing this, we're going to first find f prime of x. Okay, and we're going to do that, we're going to do the quotient rule. Then after we find the derivative, then we're going to substitute in x equals 1 to find the final answer. So by doing the quotient rule here, the derivative is going to be the denominator. Oops. Okay, go back here. Okay, it's going to be the denominator times the derivative of the top, ddx, is x squared. Again, I'm going to use, this time I'm going to use ddx. I can use ddx or I can use the prime little tick mark. Either way it works. They both mean the same thing. minus the second one, okay, or sorry, minus the numerator, x squared, times the derivative of the denominator, the ddx of g of x, all over g of x quantity squared. Okay, so then I've got this. What's the derivative of x squared? You just use the power rule to get 2x minus x squared. And then you ask, what is the derivative of g of x? Well, I don't know because I don't know what g is. So I'm just going to write it as g prime of x. And that's all over g of x quantity squared. Okay, so there's the derivative. Okay, next, so we're going to find f prime of 1. We're going to substitute 1 in for x. So I'm going to take what I did here, circling in purple, and I'm going to apply that down here. So I'm going to get g of 1 times 2 times 1 minus 1 squared times g prime of 1 all over g of 1 squared. And now I'm going to use the fact that up here, g of 1 was 2 and g prime of 1 was 6. So I know g of 1 is 2. So I have 2 here times 2 minus 1. So that 1's there. This 2 is there. That's this. And g prime of 1 from above was 6. So this is 6. That's what that is. All over g of 1, which was 2 squared. So now I get 4 minus 6 over 2 squared, which is 4. Don't cancel out the 4's. Instead, combine the numerators. So I get negative 2 over 4, which then reduces to negative 1/2. And that's my answer there. Okay. That's it for now.